Optical activity. Because the structures of enantiomers only differ in the same way your right hand differs from your left, they have the same physical properties. And physical properties are governed by intermolecular forces. And since these molecules are only mirror images of each other, molecules of R carbone are going to interact with other molecules of R carbone the exact same way that molecules of S carbone will interact with other molecules of S carbone. And this is exemplified by their melting points, which are identical, and their boiling points are identical. And you might be wondering, well, how are we able to tell the difference between R and S carbone? How can we tell the difference between these two enantiomers? Well, there's two possible ways. It says enantiomers only differ in the way that they interact with other chiral compounds and what is called their optical activity. And that's the subject of this video. Now, you might remember from earlier on in this chapter that electromagnetic radiation, or light, is comprised of oscillating electric and magnetic fields, and that each field, the electric field and the magnetic field, are located in a plane, and the planes are perpendicular to each other. The orientation of the electric field is called the polarization of the light wave. So when many waves of light are traveling in the same direction, they each have different polarization, randomly oriented with respect to one another. And that's what's going on here. We see the random polarization of light, but then we pass it through what's called a polarizing filter. And when we pass the light through the polarizing filter, only photons of a particular polarization are allowed to pass through that filter, giving rise to what is called plane polarized light. And so the light beam that's represented going through here, this is called plane polarized light. And what I have highlighted here in A and B in blue with these blue brackets here, these are called polarizing filters. So we get the plane polarized light passing through that polarizing filter. And when plane polarized light is passed through a second polarizing filter, shown here in A and shown here in B, the orientation of the second filter is going to determine whether light passes through or gets blocked. And you can see that when the second filter is aligned with the first one, like in A, that light passes through. But in B, when the second polarizing filter is rotated perpendicular to the first one, that no light passes through. Now you might be wondering, okay, well, what does this exactly have to do with organic chemistry? It says here that when plane polarized light is passed through a sample of a chiral compound, the plane that light travels on will rotate. And so what that means is if we take an enantiomer, a chiral compound, and we pass plane polarized light through it, it's going to rotate that light to a certain amount or to a certain degree. It says here that compounds that rotate plane polarized light are called optically active compounds. And we've already qualified what an achiral compound is, and so an achiral compound would not be optically active. But again, we're focusing on optically active compounds, and so chiral compounds. Back in the 1800s, scientists were exploring the nature of light by passing plane polarized light through various solutions of organic compounds. When they did that, they discovered that solutions of certain organic compounds, like glucose, for example, would rotate the plane of plane polarized light. Chemists also noted that only some organic compounds possess this quality. Compounds that didn't have that ability, again, are called optically inactive compounds. The rotation of plane polarized light caused by optically active compounds can be measured by a device called a polarimeter. And the schematic of a polarimeter is shown here in this figure. The light source over here is generally what we call a sodium lamp, which emits light at a fixed wavelength of 589 nanometers. So our sodium lamp emits light at 589 nanometers. And that wavelength is called the D line of sodium. So we take this light at 589 nanometers from the D line of sodium and we pass it through a polarizing filter. And the resulting plane polarized light continues through a tube containing a solution of an optically active compound, which causes the plane to rotate. The polarization of the emerging light can then be determined by rotating a second filter and observing the orientation that allows light to pass through. So let's see here. We have our light source, our sodium lamp. We have our polarizer. That is fixed. That is going to remain in this orientation, okay? And then when the light passes through the polarizing filter, you can see here that we only get the light in one direction, so plane polarized light. But we have our sample of our organic compound, which is chiral in this case because it's rotating the plane polarized light. And when that plane polarized light gets rotated, we can measure the degree with which it has been rotated by using the analyzer. So we rotate that, and when the maximum amount of light passes through, we measure that in degrees. Now you might be asking yourself, what's so great about this? Well, I'm just going to come up with an example out of my head. Let's say we had a chiral compound that had one chiral center and it had R stereochemistry. Let's say that compound with R stereochemistry, let's say it rotated the plane polarized light by positive 15 degrees. What's going to happen when we run the enantiomer of that compound is it's going to rotate it in an equal amount, but in the opposite direction. So it would rotate it 15 degrees. And so the relationship between these two compounds would be enantiomers. And so based off of these experiments in the 1800s, what chemists discovered is what I just said, is that enantiomers will rotate the plane of the light to equal degrees, but in opposite directions. So if one is positive, the other one will be negative. And of course, we measure the amount of rotation in degrees. When a solution of a chiral compound is placed in a polarimeter, the observed rotation, symbolized by the Greek letter alpha, will be dependent on the number of molecules that the light encounters as it travels through that solution. If the concentration of the solution is doubled, the observed rotation is going to be doubled. The same is true for the distance that the light travels through the solution, or what we call the path length. If the path length is doubled, the observed rotation will be doubled. In order to compare the rotations of various compounds, scientists had to choose a set of standard conditions by using a standard concentration, which is 1 gram per milliliter, and a standard path length, which is 1 decimeter or 10 centimeters, for measuring rotations. It's possible to make meaningful comparisons between compounds, and it allows scientists to communicate with each other. The specific rotation for a compound is defined as the observed rotation under these standard conditions. 1 gram of compound dissolved in 1 milliliter solution, passing through a path length of 1 decimeter. Well, it's not always practical to use a concentration of 1 gram per milliliter when measuring the optical activity of a compound, because chemists often work with really small quantities. Like, let's say you had only 10 or 15 milligrams or even 1 milligram of a compound. Very often, optical activity must be measured using really dilute solutions. To account for the use of non-standard conditions, the specific rotation can be calculated in the following way, using this formula right here. And in this formula, alpha in brackets represents the specific rotation, alpha in the numerator represents the observed rotation, C is the concentration measured in grams per milliliter, and L is the path length measured in decimeters. In this way, the specific rotation for a compound can be calculated for non-standard concentrations or path lengths. The specific rotation of a compound is a physical constant, just like a melting point or a boiling point or a density. The specific rotation of a compound is also sensitive to temperature and wavelength, but these factors cannot be incorporated into the equation because the relationship between these factors and the specific rotation isn't a linear relationship. In other words, another way of putting that is like saying doubling the temperature doesn't necessarily double the observed rotation. In fact, it can sometimes cause a decrease in the observed rotation. The wavelength chosen can also affect the observed rotation in a nonlinear fashion. Therefore, these two factors are simply reported in the following format that's shown right here, where T is the temperature in degrees Celsius and lambda is the wavelength of light used. And so if we looked at these two enantiomers here, R2-bromobutane and S2-bromobutane, you can see that their optical rotations are equal but in opposite directions. So for R2 bromobutane, it's minus 23.1 degrees. And for S, it's plus 23.1 degrees. And both of these samples were run at 20 degrees Celsius. And the wavelength was 589 nanometers because the letter D here represents the D line of sodium. Let's talk about this positive and negative rotation some more. A compound exhibiting positive rotation is called dextrorotatory, while a compound exhibiting a negative rotation is called levorotatory. The descriptors R and S refer to the configuration of the chiral center. In contrast, the positive and minus refer to the direction in which plane polarized light is rotated, which is dependent on the conditions at which it is run. As an example, consider the structure of S-aspartic acid that's shown here, which has one chiral center. The configuration of this compound is going to be S no matter what, but the optical activity of the compound is very sensitive to temperature. It's levorotatory at 20 degrees Celsius, but it's dextrorotatory at 100 degrees Celsius. This example illustrates that we can't use the configuration R or S to predict whether a compound will rotate plane polarized light in the positive or the negative direction. The magnitude and the direction of optical activity can only be determined experimentally. The magnitude and direction of optical rotation cannot be predicted and has to be measured experimentally. A solution containing a single enantiomer is said to be optically pure or enantiomerically pure. That is, the other enantiomer is entirely not there, it's just absent. A solution containing equal amounts of both enantiomers, or a 50-50 mixture of both enantiomers, is called a racemic mixture. And what happens is when we measure the optical rotation of a racemic mixture, we find that it is 0 degrees. Let's say, for example, we had an R stereoisomer that had an optical rotation of, let's say, let's just pick plus 30 degrees. Well, if it's a 50-50 mixture with the S enantiomer, which would rotate plane polarized light minus 30 degrees, we have plus 30 and minus 30, and they cancel each other out, and so we end up with no optical rotation. However, if one enantiomer is present in excess, that means there's more of one enantiomer than another. They're not in a 50-50 mixture. It's not 100% of one, so we just have an excess of one relative to the other. Then the mixture is going to have optical rotation, but it's going to be less than the pure enantiomer. So it's going to be rotated in the direction, whether it's positive or negative, it's going to be rotated in the direction of the enantiomer that's present in excess or present in a greater amount. And what's interesting is that when you have unequal amounts of enantiomers, the enantiomeric excess, or the percent EE, can be determined from the optical rotation. So let's take these two compounds, S and R, 2-bromobutane. And let's suppose we had a mixture of R and S, 2-bromobutane, that has a specific rotation of minus 4.6 degrees. Since the R stereoisomer rotates plane polarized light in the negative direction, we know that we have an excess of the R stereoisomer. And we can use this formula right here to help us determine the percent enantiomeric excess of that enantiomer. So we put the absolute value of our observed optical rotation, which is 4.6 degrees, and we divide that by the absolute value of the optical rotation of the pure enantiomer, which in this case would be 23.1, and then we multiply that by 100%, and we find out that we have a 20% enantiomeric excess. That means we have 20% more of the R stereoisomer than we do the S stereoisomer. Now we've got a 20% enantiomeric excess, and we're going to have more of the R stereoisomer, right? Because our optical rotation was negative, like that of the R stereoisomer. Well, we know the total of the two stereoisomers, of the R and the S, we know that R plus S, the total of both of those is going to add up to 100%, but we know that we've got a 20% excess of the R, so we know that R minus S is going to be equal to 20%. And so if we add those two up, we can see that the S's are going to cancel out, and we get that 2R is equal to 120%. And then we can, from there, we can divide both sides by 2, and then we can determine that R is actually equal to 60%. Now, if they add up to 100%, what plus 60% gives me 100%? And the answer is that the S must be present in 40%. Here's a summary of what you need to know from section 5.4 for Organic Chemistry 1. First, you need to understand the basic concepts and terminology of plane polarized light and polarimetry. You're not going to have to calculate specific rotations or enantiomeric excesses, and so you will not have to use any of the formulas or apply those formulas, but you should know what is meant by the terms optically pure, enantiomeric excess, and when we have a 50-50 mixture of enantiomers, we call that a racemic mixture.